These are the corrections for midterm homework question 3. Okay, so again, starting off with a question like this, I think the best thing to do is focus on the reaction scheme they've given you and see how much information you can gather yourself from that. This first molecule has 2 carbons and an OH group, so that must be eth and then anol. So it's an alcohol with 2 carbons in it, ethanol. Then conversion X gives me B, and if I was to draw out B, I can see that it's 2 carbons bonded together, 4 hydrogens, which gives each carbon 3 bonds around it, and it needs 4. It has a valency of 4. So there's going to be a double bond in there, and 2 carbons, making it ethene. And now if I go back to conversion X there, how do I get from an alcohol to an alkene? What have I done there? That's an elimination reaction. So that reaction X is an elimination reaction. And what I have done is minus H2O there. Next then we go from B to C, and C, if I was to draw that out, will be 2 carbons bonded to each other, 6 hydrogens around them, and that satisfies all of the outer shells of the atoms there. And so that one is ethane. And now looking at my reaction scheme, so reaction Y is going from ethene to ethane, and so that's going to be an addition reaction. You can see that from the 2 I've drawn out there. I've added H2. I've added 2 hydrogen atoms across that double bond. Next, compound D is the same as ethane, except one of the hydrogens has been replaced by a chlorine molecule. So when I'm looking at that one, I am seeing that this is ethane, but one hydrogen is now a chlorine atom. So that's going to be chloroethane. Now I could put 1 chloroethane there. Again, it doesn't matter here because with something that has only 2 carbons, no matter which way you put it on, when you name it, it would be 1. And that conversion from an alkane to a chloroalkane, so Z there, that's going to be my substitution reaction or my free radical reaction. And what I have done there is I have added Cl2, so that would be my reactant there. I know that I've only added 1 chlorine atom to the ethane, but remember that my reactants there would be Cl2 and UV light would be necessary too. Next then, E is our last compound to name, and that one is ethane again with 2 bromines attached to it. So 2 of the hydrogens have been replaced with bromines. So that is going to be dibromo, because there's 2 bromines. Dibromo, 2 carbons means it's ethane. So dibromoethane. And in order to name it properly, I do need numbers to signify where these bromines are. And my answer for that comes if I go first and look at reaction W here. So to get from an ethene to the dibromoethane that we've got, that's going to be an addition reaction. So an addition reaction across that double bond. And what we're doing is we're adding Br2. Forgot my 2 there. We're adding Br2 across that double bond. And for our mechanism that you have to know for this, we get the 1,2 dibromoalkane. So if I just draw that out, it might make more sense. So this is my alkane, and when I undergo the addition of Br2, so the addition reaction W there, what I'll end up with at the end of that mechanism is one bromine on each. So this will be called 1,2-dibromoethane. Ethane. Okay, now when we get onto the questions, hopefully we'll see that we've actually answered most of these already. Question A is asking us to classify each conversion as addition, substitution, or elimination. We have done that already. W was addition, X was elimination, Y was addition, sorry, I'm trying to remember. Z was the substitution then. B, they're looking for evidence for the free radical mechanism. So they haven't asked us to draw the mechanism or write it out. They've asked for the evidence. So again, there's lots of different options for your answer here. One piece of evidence is that UV light is required to initiate the reaction to create the radicals in the first place. The next one was that other substances are produced, so other products are produced that wouldn't be produced if you didn't have free radicals. I suppose other ways actually that I could add in there for the UV thing is that for every photon that is emitted, the hundreds of products are formed, so that even if you stop the UV light, the reaction will keep going on. So again, I'm maybe not writing it in the same way. I can send you the link to the mark scheme for this answer as well. Then the other thing is that the reaction won't occur in the dark because UV light is required. Finally, the other thing that we could mention there is that the addition, so adding tetraethyl lead speeds up or alters the rate of the reaction. And the reason for that is because tetraethyl lead is a known source of free radicals. Next, so name the reagent and catalyst required to convert B to C. That was converting the alkene to the alkane. And what we need there, I wrote alkene again. What we need there is hydrogen and a nickel catalyst. D, after carrying out the conversion of A to B, how would you test the product to confirm the formation of B? And so here they're asking us for the test for unsaturation, because we know that B is our alkene, so there's a carbon-to-carbon double bond in there, which means that the compound is unsaturated. In comparison, if I just put over here on the side, we started off with the alcohol, which is totally saturated. Around the carbons they're all tetrahedral carbons with 4 single bonds, so that is fully saturated. The alkene is not. And there's 2 different ways we can test for unsaturation. That would be with bromine water or with acidified potassium permanganate. And the result would be the same for both of those. They would go colourless. Now there's only 6 marks here, so I'm not sure, looking at this straight away, how much information do they want me to give? I would say 6 marks. They're looking for me to name one of these, so to name one of the compounds, and the result, that it'll turn colourless. But just to give as much information as we can here, I'll also add in that bromine water is a reddish brown colour to begin with, and KMnO4 potassium permanganate is purple, and they'll both turn colourless in an unsaturated solution. Part E is looking at chromatography, so describe with the aid of a label diagram the separation of a mixture using one of these three types of chromatography. We chose paper chromatography. So to start out our diagram, we'll show the gas jar that our experiment is going to happen in. Within that, we are going to have our solvent down at the bottom. And so we want to make sure that we label that. That's our solvent, which is the mobile phase. Again, you probably wouldn't need to write that in, but we'll just give the detail to recap it all. Next, I want to put in my chromatography paper, and I want to show that this reaches the solvent. So the bottom of the chromatography paper has to be in the solvent, and that it's suspended there as well. So that's my chromatography paper, and that's my stationary phase, if I just want to add in a bit more detail there to recap it. Next, I'm going to be very careful here when I'm showing where the line that my mixture is on is going to be. I want to make sure that I show that the line where I'm putting my mixture is well above that solvent line. I want to make sure, as I'm highlighting there, that there's space in between those. You have to show that to show that you know that the mixture can't be in the solvent, otherwise it will dissolve into the liquid solvent down at the bottom and it won't travel up the chromatography paper. The last thing that you need to show here is how the mixture separates. You can do that by showing some separation on your diagram. You can show some dots here and label them as your components of the mixture. So we can label that as components. Or you could, if you thought that that would get messy, you could write a sentence saying the same thing, that as the mixture is drawn up the paper by the solvent, the components of the mixture will separate out based on their adsorbance to the chromatography paper. Part 2 we touched on briefly there. The reason that the different components travel different distances is due to their different adsorptions or their interactions. It's to do with the intermolecular forces between the components and the paper. So the different adsorptions or interactions between the mixture and the mobile phase. I should have said stationary phase there, sorry. And part 3, what use is made of chromatography in forensic science? And that's to identify ink or dyes taken from crime scenes.